Log on, tune in, find out. Another good idea from Cambridge.
Cell decompositions, moduli spaces, and generalisations.
Thanks. So I realize that I have a little bit of a difficult job ahead of me because I'm really more of a topologist, and I'm trying to speak to a room full of people who are essentially algebraic geometers. So the way this story goes, though, is it starts off with some things that happen in algebraic geometry, or at least complex analysis, and it goes off from there into other realms. So the moral of the story, I guess, is that topologists should say thank you to some of the people who thought up these ideas for giving us some interesting things to work with. The story starts with ribbon graphs. So a ribbon graph is just a graph. I'll assume you all know what a graph is. Equipped with a cyclic ordering of the edges. I can't speak and write two different things at the same time. A cyclic ordering of the edges incident at each vertex. So you have a vertex, you have some edges coming in like that, and you give it a cyclic ordering. Now, if you have this data, then you have a canonical way to thicken the ribbon graph into a topological surface. You just replace each edge with a little strip. And those all glue together and make some topological surface with boundary. And it's oriented, because the cyclic orderings on each of the vertices give you a local orientation here, and you can transport that around along the edges. So that's what a ribbon graph is. Now, these ribbon graphs give a way of turning questions about the topology of moduli spaces of Riemann surfaces with marked points. Oh, it's oriented here, and the orientation agrees with the orientation there, because I've glued in the strip without a twist. There's some other...
But you're picking a compatible ordering at the different vertices.
However you pick the orderings, they're automatically going to be compatible if you glue the strips in the right way. The compatibility of the orderings determines the way to glue the strips.
If the graph is trivalent, then you're saying it's automatically the surface is oriented.
Oh, okay, I'm going to assume for now that my graphs don't have any bivalent or univalent edges.
Yeah,
They're at least trivalent. Yeah, at least trivalent at each vertex.
Then this surface is automatically oriented.
Yeah, or automatically oriented.
Can't you take RP2 and put a trivalent graph on it? And then if it's trivalent, then you already have these orderings.
You have a cyclic ordering for a graph on RP2, except you don't know which way is clockwise. So it's an equivalence class of orderings.
But you said nothing about compatibility at different vertices.
Yeah, the compatibility determines how you have to glue the strip in.
So there is a condition.
No, the compatibility isn't a condition on the orderings of the vertices. The compatibility tells you how to thicken it into a surface.
It's not compatible. He can.
Yeah, if they were not compatible, then it's just because I glued this strip in with a twist, and I should have twisted it one more time to make them compatible.
But you can go off on RP2. You can do this, but it doesn't give you RP2 back. It gives you some other.
But for trivalent, there is no choice. I mean, whatever orientation you pick, you get
Here,
there.
I'm going to move on, and we can come back to this. So, ribbon graphs give a method for converting questions about the topology of the moduli space of genus G Riemann surfaces with n marked points into combinatorics. Well, combinatorics of ribbon graphs. Now, ordinarily, combinatorics can be easy or hard. I'm not making any value judgment here about whether or not the combinatorics you get out of this is easier or harder. But but you can often solve problems using the combinatorics. And some examples of the sorts of problems you can solve are, well, there is a calculation of the Euler characteristic of, I'll just give you the case for mg1. The orbifold Euler characteristic of mg1 is the Riemann zeta function evaluated at 1 minus 2g. So this is a beautiful theorem of Herrer and Zagier, and then Kontsevich later gave a different argument that streamlined the computation a little bit. But this is an application of using this ribbon graph combinatorialization of the moduli space of curves. Another computation also or another result using ribbon graphs by Kontsevich was Kontsevich's proof of Witten's conjecture on intersection numbers. So Witten, by comparing two different models for quantum gravity, conjectured that the intersection numbers on the Deligne-Mumford compactification, you could make a generating function, and this generating function would satisfy the KdV hierarchy, which gives you an inductive way of computing these numbers. And Kontsevich proved that theorem, and the proof he gave went by way of ribbon graphs. So what's behind all of this is the fact that there's a cell decomposition of, well, there's a cell complex with cells labeled by ribbon graphs. And this cell complex is homotopy equivalent to the moduli space of Riemann surfaces. So let me first define something. A metric on a graph is a length on each edge. Just assign a non-zero real number to each edge. Now we have a space. Let me write m gamma rib gn. This is the moduli space of metric ribbon graphs. So how do you fit these things together? Well, here's a little piece of a ribbon graph, and suppose I have some length L here. As L goes to 0, then you just contract that edge, and you get this ribbon graph. So it fits naturally together. This is a cell complex.
I'm sorry. It only fits naturally together if the orientations of those two vertices are compatible. If they are not, then it doesn't.
Well, suppose I chose this cyclic ordering here and this cyclic ordering there.
Yes.
Right. So let me call these edges A and B. Then I've just drawn the picture wrong. I should flip this over. I should twist this edge here. So A and B are swapped. And then I have the opposite cyclic ordering. It's compatible. So the compatibility is just a choice of the way you draw it, not an actual condition on the orderings. Okay, so each cell corresponds to an isomorphism class of ribbon graphs. And each cell is just, the coordinates on the cell are just given by the lengths of all the edges. So it's a Euclidean space. It's cells correspond to graphs, and cells are diffeomorphic to r greater than 0 to the number of edges. Okay, so this is our combinatorial object. And over here, the theorem is that this combinatorial object, this moduli space of metric ribbon graphs with n boundary components and the genus G, is homotopy equivalent to the moduli space of Riemann surfaces of genus G with n marked points. So, beautiful theorem. There are many slight variations on it, and there are many different people who were involved in proving this in many different ways. Let me try to summarize all the different directions you can come at this. So the first way you can come at this theorem, or maybe the oldest way, was from complex geometry, or at least complex analysis. And this is by way of Strabel differentials. And there's a proof of this theorem. I suppose it wasn't really written down until Giansiracusa spelled it out. But his credit sort of goes to Mumford, Thurston, though I don't know if he used the Strabel differentials, or at least I don't know if he had the Strabel differentials in mind. Giansiracusa is the one who actually wrote this down first, to my knowledge. And, Harrer also gets some credit in there. So that's method one for proving this. In fact, this method proves something a little bit nicer. It proves that if you cross this mgn with r to the m, then you get actually a homeomorphism there, a homeomorphism of orbifolds. So this method is nice in that way. It gives you something a little bit stronger. But there are other methods also. So coming from the point of view of hyperbolic geometry, there's a proof of this by Penner. According to Penner, essentially, Teichmüller space is the space of ideal triangulations. Teichmüller space is the space of ideal triangulations of the surface, where the vertices are the marked points. There's then much later another point of view, which goes back to using some tools from well, I suppose you could do this one in terms of hyperbolic geometry or in terms of the complex geometry. This is the method that Kevin Costello described. And so this one uses compactifications of moduli spaces, I'll say. It's a beautiful argument where he says, define a partial compactification of your moduli spaces, and then define a certain flow. And the flow simplifies simplifies the surfaces occurring in this moduli space to something a little bit more degenerate. And you iteratively apply this flow again and again, and eventually your surfaces are reduced down to pieces which are essentially the vertices of a ribbon graph. So it inductively reduces everything down to ribbon graphs. Costello's argument just gives you the homotopy equivalence. It doesn't give you the homeomorphism that these other two methods give.
You need n to be positive.
For all of these, you need n to be positive. There's no known cell decomposition yet if n is 0. What I want to talk about is a different method. Which uses topology of surfaces in a very naive sense, just very simple things and combinatorics. Easy combinatorics. So this is my own particular viewpoint on this. Now, I know the audience here, you're all wondering, well, what's wrong with these methods? But the reason it's nice to have a different viewpoint here is because I love this theorem so much that I want to prove a similar thing in settings where I don't have the wonderful tools of Strabel differentials or hyperbolic geometry. I don't have all this beautiful theory to play with. All I have is some vaguely combinatorial things that look like what might be underlying all of this. And it turns out that these combinatorial structures are enough to prove the theorem. So that's what I want to talk about, how to extract just the combinatorial skeleton behind this proof. So the application I have in mind is the world of three-dimensional handle bodies, where, of course, you don't have moduli spaces of geometric structures on handle bodies in the same way, or at least finite dimensional things. And so you really need a method different from the top three. So let me describe, well, before I get on to handle bodies, let me describe how you prove this theorem in the surface case. Let's have S a surface, genus G, n marked points. I'll call the points P1 up to Pn. An arc in S is it's an embedded curve with endpoints at the marked points. And so it meets the marked points only at the endpoints, and the rest of the curve has to be inside the surface minus the marked points. And there's one extra condition, which is the arc doesn't bound a disk. In the surface. Okay, the arc complex is a combinatorial gadget. It's a simplicial complex that's been used in low-dimensional topology for many, many years. A wonderful, beautiful thing. It's defined as follows. I'll call it A of S. It's a simplicial complex. Vertices are isotopy classes of arcs in S. And n-simplices are isotopy classes of disjoint n-tuples of arcs in S. And they have to be not pairwise isotopic. Oh, that's interesting. I should have said here, doesn't bound a disk in S. I think I said this wrong. Doesn't bound a disk or a once punctured disk. In S minus the marked points. Okay, so we have our simplicial complex here. Now, it's very similar to something that also gets used a lot called the curve complex. The curve complex, you prove all sorts of wonderful theorems in surface theory using the curve complex and the fact that the curve complex is highly connected. There's a similar statement about the arc complex. The arc complex is actually contractible. But this is a much easier result. It's contractible. This goes back to Hatcher and McCullough. Now, contractibility, or the connectivity estimate for the curve complex, where you use closed curves instead of arcs, that's a very deep theorem, very hard to prove. This contractibility is very easy. In fact, it's so easy I can show you how to prove it in just a few minutes. What we're going to do is construct a deformation retraction of this complex down onto the star of a vertex. So a vertex in the arc complex means an arc. And the star of the vertex is all of the collections of arcs which don't meet, which are disjoint from this particular arc. So sigma is in the star of V if and only if arcs of sigma are disjoint from the arc V. Okay, well, let's suppose that we have some arbitrary simplex in the arc complex, which isn't necessarily in the star. Well, let me draw V there. Then the arcs of this simplex sigma will be some arcs. Some of them might be far away, and some of them might cross V. And a point in this simplex corresponds to giving these some weights, T1, T2, T3, such that the sum of these weights here plus all the other weights for all the arcs which don't meet V adds up to 1, but let's not worry about that. Now what we're going to do is try to move through this simplicial complex so that eventually all of these arcs don't meet V anymore. And it's the simplest possible thing. You just say, well, if I want to get these arcs off of V, I just snip them. I just take my scissors and run my scissors along V and gradually snip. So S will be the parameter for our deformation retraction, our homotopy. So what you do is you replace this with, there's the arc V still, and I start with the first arc in this list, and I replace it with, all right, I cut along V. I cut this first arc there, and I replace it with two new arcs which go up to this, this vertex of V here. And I have my old arc, and I have the other two. And now this still has weight T3, this still has weight T2, and the weights on these two, so I have both this first arc and the surgered version of it, will be S times T1 and 1 minus S times T1. And so you run S from 0 to 1, and the weight shifts from this arc here to this arc here, and you're one closer to being inside the star of V. And you do that for the second one and the third one. So when S equals 1, then you've got this picture. And now I do the same thing again for the second arc that's causing me trouble, and then the third arc. And eventually, I've pushed all of the arcs off of V, and so I've moved every point in this simplex sigma into the star of V. And since the star of a vertex is contractible, star of anything is contractible, this deforms the whole space into the star of a single vertex, and you're done. So that's how you contract the arc complex. That was Hatcher's argument.
What if the begins at the top vertex and ends at the bottom vertex? And how is using the factor?
So now a simplex sigma, I'll call it complete, if the arcs of sigma divide my surface S into a bunch of disks. So you cut the surface along all the arcs, and all you have left is genus 0 pieces, and there's a slightly technical stability condition here, which is that each disk meets at least 3 arc sides. So what I mean by this is, for instance, yeah?
So you have some complex, and you have a vertex. Are you saying the star is always contractible?
It's a simplicial complex, yeah.
Simplicial complex. If I take a ball, and take a center for my vertex, and just triangulate, right? And then the star of that vertex, wouldn't that be the sphere?
Um,
And isn't the sphere not contractible?
yeah, is that not quite giving you a simplicial complex?
So I'll just take the vertex.
Because you have what you have there is multiple edges going between two vertices. So that isn't exactly a simplicial complex. You'd have to subdivide it a bit by adding more vertices. You have a vertex here and a vertex here, and you're saying, well, I've triangulated it, so I have some edges like that.
Let's just take a disk, two-dimensional disk, take the center of that disk and just triangulate it, like an orange.
Mm-hmm.
And my vertex is the center of that disk.
Yeah.
And what I see is that the star is the circle.
Yeah.
And circle is not contractible.
That's the link you're thinking of.
Oh, it's still. Oh,
The link is the boundary of the star.
It's star, it's not the link. Okay.
Yeah.
Thanks.
Yeah, the star is just the union of all the simplices which contain the vertex.
Certainly contractible.
Okay. So I told you what a complete simplex is. So these are the ones we want to focus attention on. And now I'll write A naught of S is the poset of complete simplices in A of S. Okay, so this is a poset. You can take its nerve to get a topological space again. So easy proposition is that the realization of the nerve of this poset is also contractible. And the way you prove that is by contractibility of the full arc complex and induction on the genus and the number of marked points. So very, very easy argument there. Just a couple of lines long, really. But the point now is that this poset of complete simplices is much more closely related to ribbon graphs. So now, well, first of all, if we're interested in the moduli space of Riemann surfaces, then you can construct this as Teichmüller space modulo the action of the mapping class group of a surface. The Teichmüller space here is contractible. And so this tells you that as an orbifold, the moduli space is homotopy equivalent to the classifying space of the mapping class group. So if we're just interested in the homotopy type, I can replace my moduli space of Riemann surfaces with just classifying space of the mapping class group. We're reduced to studying this very complicated group, the mapping class group. Now, the reason for trading the moduli space with the mapping class group is because the mapping class group now has a direct relation with the arc complex of the surface. So the mapping class group acts on, well, it acts on the arc complex and it acts on this poset of complete arc systems. So I can take the topological space represented by this poset, and I can take the quotient by the mapping class group. The action isn't free, so I want to take the Borel construction, or the homotopy quotient. So if I write this, since this space is contractible here, this homotopy quotient here, this Borel construction, is homotopy equivalent to B of the mapping class group of my surface S. Now, on the other hand, this thing here is directly and immediately related to ribbon graphs because of a wonderful little theorem of Thomasson. So what we have here is a group acting on a poset. And there's a model in terms of the nerve of a category for this Borel construction that Thomasson gave. And the model says this Borel construction is homotopy equivalent to the geometric realization of the nerve of some category. And the category is, it's written like this, and then I'll tell you what this means. This category here the objects are just the complete arc systems, the complete simplices of the arc complex. Hom in this category from some complete system of arcs sigma to some complete system of arcs tau is the set of pairs of F, an element of the mapping class group, and then it's just the set of elements F in the mapping class group such that F of sigma is a subsimplex. It's less than tau with respect to the poset structure here. So it's just a set of elements in the mapping class group. And you can figure out how to compose these things. Compositions are induced by composition of elements in the mapping class group. Okay, so this is some discrete category. And we're taking the nerve of this category and the geometric realization. Now, here's the key observation. If I have a complete simplex in the arc complex, then it determines a dual graph, which is exactly a ribbon graph. So if I have a complete system of arcs, let's call this alpha 1 up to alpha k, then the dual graph of this decomposition of this system of arcs is a ribbon graph. Well, let's see how that works. If I have a vertex there, and a vertex there, and here's an arc alpha 1, here's an arc alpha 2, and here's an arc alpha 3. Maybe I should get some colored chalk for this. Then the dual graph here has one vertex for each disk in the complement of the arcs, and one edge for each arc. So there's a little piece of the ribbon graph. And the orientation of S determines my cyclic ordering of the edges incident at this vertex. So you get a canonical ribbon graph structure on the dual graph. Okay, that builds a ribbon graph for us. Now, we look over here, and you just take a moment to think about what this category is. Well, what's going on here is objects are these arc systems, the complete ones, essentially the same thing as ribbon graphs. You can go backwards. If you have a ribbon graph sitting inside your surface in a homotopy equivalent way, then it determines a dual arc system. So you can jump back and forth between either picture. This category here is exactly equivalent to the category of ribbon graphs. So this, as a category, this is equivalent to category of ribbon graphs. Of type G, M. Okay, so we're taking the nerve of the category of ribbon graphs and taking its realization, and it's not too hard to see that that's a model for the moduli space of metric ribbon graphs. So in general, you take some cell complex like this, and you take the category of inclusions of cells, and the nerve of that category geometrically realizes to something homotypically equivalent to what you started with. It's just like for a simplicial complex, if you take the poset of simplices and then the nerve of that, then that's just a barycentric subdivision. Okay, so the key point, though, is to observe that this category in here, which models the Borel construction, is just exactly the category of ribbon graphs. And that's it. Now, the reason for showing you this is so that I can say why, say how to generalize this to some situation like 3 manifolds, where we don't have any of those other nice tools. So let me describe what you can do that's analogous to this for handle bodies. Well, there's one thing you can do before we go to 3 dimensions, is you can replace Riemann surfaces with Klein surfaces. Klein surface is like a Riemann surface. It's a topological 2-manifold with something like a complex structure, except the change of coordinates are not complex analytic. They're either holomorphic or anti-holomorphic. So it's an unoriented version of complex surfaces. So if we want to talk about the moduli space of Klein surfaces, then on the other side, you just replace the ribbon graphs with something that I'll call Mobius graphs. So a Mobius graph is just like a ribbon graph, except now this is exactly what Valerie was worried about earlier. We don't have a cyclic ordering at each vertex. You just have a cyclic ordering up to flipping the direction and adding a twist to all the edges around it. It's an obvious notion, and if you're curious, we can talk about it later. I'll leave it to you to work out if you want. So that's one direction, but you can prove the same theorem using all the other methods, using Costella's method, using Penner's method, using the Strabel differentials method, I think. So this is nothing really new, other than I think nobody bothered to write it down until very recently. A student of Andrei Lazarov, Chris Brown, wrote down the analog of Costella's proof method to prove that the moduli space of Klein surfaces is homotopy equivalent to the moduli space of Mobius graphs. But the second generalization, I don't know of any way using the previous proofs to prove this. And this is, well, the handle body, or 3-dimensional handle body mapping class proof. Is modeled by the space of metric graphs with something that I like to think of as an S2 ordering at each vertex. So S2 is the two-sphere. Let me tell you what I mean by this. Well, at a vertex, I have some incoming edges, and I decorate this vertex by a two-sphere, and I think of each edge as corresponding to a little disk lying somewhere on that two-sphere. And these disks are they're actually embedded disks. They not just submanifolds. They're actually parametrized by a standard D2. So you decorate each vertex with this data, a configuration of disks sitting inside the two-sphere. And when an edge contracts, then you connected sum, as I contract this edge here, you connected sum the two spheres together along the two disks that are meeting, and that gives you a new configuration of disks on a new two-sphere. So the idea here, oh, I should say what a handle body is. This is a three-manifold with boundary. The boundary is a surface, and it's made by attaching one handles to a three ball. So it's something where if you draw a picture, it looks like this, except it's now a solid thing. It's like a lump of dough, and you've punched some holes through it with your thumb. Right? It's a three-manifold with boundary here, and you're just seeing the boundary because the interior is on the inside. So let me refer to my handle body as K. So now, instead of using arcs in a surface, we use disks inside K. So here's a little piece of my handle body. A disk it's a D2 sitting inside K with the boundary of the disk sitting inside the boundary surface of my handle body. The theorem of Hatcher and McCulloch, using exactly the same argument, says that if you make a complex of these, you get a simplicial complex of systems of disks in your handle body, and Hatcher and McCulloch proved that this disk complex is contractible. Argument's essentially exactly the same. You do this little surgery trick to push everything down into the star of a vertex. Now, I'll define a poset of complete simplices in this complex, where complete here means the complement of the disks is a bunch of three balls. So exactly analogous to what we did with complete systems of arcs. And exactly the same little inductive argument tells you that this poset is also contractible. Now, the reason for passing to the complete simplices instead of the arbitrary simplices is, again, because we have dual graphs. Again, the vertices correspond to components of K minus the disks in this, sorry. Yeah, so the dual graph of a simplex sigma, of course, the vertices of the dual graph correspond to the components of K minus the disks in the simplex sigma. And the edges, as before, correspond to the disks. Now, the situation is a little bit different here because when you pass from the simplex, or from the system of disks, to its dual graph, you're actually losing a little bit of information because you don't know how to replace the vertices with 3 balls and glue them all back together to recover your handle body. And the information you're losing is exactly the configuration of disks on the boundary of the 3-ball. So the information you're losing is exactly this labeling of the vertices that I mentioned earlier. So just to spell this out a little bit here, the mapping class group of the handle body acts on this poset of complete disks. And since this thing is contractible here, B of the mapping class group of the handle body is homotopy equivalent to the Borel construction of this poset cross over the mapping class group with E of mapping class group. Now, by Thomason's theorem, this is the realization of the nerve of some category. And the category is written mapping class group of K. It's this thing here. Objects are the complete disk systems. And a morphism, as before, is an element of the mapping class group which sends one complete disk system into another. So exactly analogous to what we had before. Now you can look at what that's doing on dual graphs. There's a functor from this category. You can view taking the dual graph as a functor to the category of graphs. That functor induces a map from the realization of the nerve to the realization of the nerve. This, by the way, happens to be a model for the group of outer automorphisms of a free group of rank G, where G is the genus of the handle body here. That's just a little side comment. Put that in parentheses. But you look at this dual graph functor, which I'll call gamma, and you examine the fibers of gamma. And you see that the fiber over a graph gamma is pretty much, I'll say, the space of labelings of vertices by these S2 configurations, these configurations of disks in the T-sphere. Now, let me explain these quote marks here. It pretty much means there's a little detail that I'm sort of brushing under the rug here. And this little detail is just to do with the framings on the disks. So the little detail is just that if I have a disk, and on one side there's part of the handle body, on the other side there's part of the handle body, this disk doesn't come with a parameterization. And so when I cut along it, I don't know how to parameterize the two disks on either side. I just know that if I change the parameterization on one side, then I have to change the parameterization on the other side by an equal and opposite amount. And that little detail is actually miraculously taken care of if you allow disks to possibly be parallel to each other. And so you talk about disk systems where your graphs are allowed to have bivalent edges. And then it just beautifully works out, actually. By integrating out the bivalent vertices in the graph, you exactly take care of this problem of gluing together the parameterizations on either side, or modding out by the equivalence of changing the parameterization on one side and changing it oppositely on the other. It just takes care of itself by integrating out the bivalent vertices. So I should state a concise theorem here. So B of the mapping class group of this handle body is homotopy equivalent to the moduli space of graphs of, if this is a genus G handle body, moduli space of graphs with the first Betti number equal to G, and this S2 decoration, which is not, in the case of ribbon graphs, that was a discrete datum. It was just a choice of cyclic ordering, which is a discrete thing. Here now I have a topological thing. There's a whole space of labelings I can attach to each vertex. If you know the language of operads, this is the same thing as framed little two-disks graphs. So it's a space of graphs with vertices labeled by appropriate elements of the framed little two-disks operad. And there's an operatic way of interpreting this statement, which I find very attractive, but I think you have to have been inducted into this sort of language of operads and become a kind of groupie to like this. But I'll just tell it to you. The statement is that if you start off with the framed little two-disks operad, then it's a cyclic operad. And a cyclic operad generates a modular operad. So a cyclic operad is a thing where you have operations with several inputs and one output. But I'm allowed to rotate the picture, so my output becomes an input and one of my inputs becomes the output. That's a cyclic operad. A modular operad is something where you're also allowed to glue the output to one of the inputs. You can contract things like that. A cyclic operad generates a modular operad. And if you ask what modular operad does the framed little two-disks cyclic operad generate, it generates the modular operad you build from B diffs of three-dimensional handle bodies. So that's the operad statement, but this is, I think, the wrong place to advertise that sort of result, so I won't write it down. Thank you very much.
Questions?
Now Valerie has no questions.
So do you recover just the homotopy equivalence, or do you also get a statement of homomorphism when you cross with a...
No, you don't really, you don't get a homeomorphism. Well, no, I should say, the theorem that I wrote down there says B of some group is homotopy equivalent to something. But the classifying space of a group is really just a homotopy type, so.
even for the original problem, the original theorem for moduli spaces.
Yeah. Yeah, so this method ends up being essentially, it gives you the equivalent statement to what Costello proves, which is that the moduli spaces of Riemann surfaces with the open string type glowing form a modular operad, and that modular operad is homotopy equivalent to the modular operad of moduli spaces of ribbon graphs. So that's the statement that Costello proves. He also gets some other interesting statements about it. But I just recovered that part of Costello's theorem. Yep.
Yeah, so the, so it's behind you on where you're standing there. So the arc complex definition,
Yeah.
that will definitely apply all the way through could apply through a biological system where we're talking about N neurons interconnecting, and axons interconnecting. It could apply.
I'm not sure how to answer.
I think talking from a biological point of view, but given that in any neuron system there's people, you defined it as alpha 1 to alpha n.
Yeah, so it's arcs connecting up the marked points and dividing the surface up.
I'm quite confident that this definition could apply to a biological system like that.
If the biological system can produce a surface, I mean, you somehow out of your biological system you produce a surface, and you can write down the arc complex for that surface.
For example, a photograph, a two-dimensional photograph of a biological system.
I'll go ahead and say, yes, you can write down this definition anywhere where it makes sense. And I showed you how to prove that in the case of surfaces, in the case of hyperbolic surfaces, negative Euler characteristic, then the complex you get will be contractible. In other settings, I don't know if it's going to be contractible or not.
More questions? Then can we thank the speaker again?